Hi, welcome back to the Radio Merit Badge. These are requirements 4 and 5C about how radio waves are modified to put information on them. We said at the very beginning when we defined what radio was that you needed a transmitter and a receiver. There are a couple other things that you also need. The transmitter, to review again, generates the signal or the carrier that the information is going to be put onto before it gets sent to the antenna. The feed line is the actual cable or wire that carries the carrier with the information to the antenna, goes from the transmitter to the antenna. The antenna is a wire up in the air or a pole or some kind of metallic device that's conductive that actually takes the signal from the transmitter and feed line and sends it out over the air. At the other end is a receiver that actually takes the radio signal with the encoded information on it, strips off the radio carrier, and extracts the information and presents it in a form that we can understand or read or see. These days, those functions of transmitter and receiver are generally combined into one unit, and that's called a transceiver. Our phones essentially are transceivers. Our two-way radios configured as cell phones are transceivers. They have a transmitter and a receiver built into one unit. Sometimes we need to use a lot of power to get a signal out onto an antenna to be able to communicate over great distances or to cover large areas. And we would be using an amplifier that would be fed by our transceiver or our transmitter. That would feed a feed line, and that would send the signal up to the antenna. This is a picture of some vintage equipment where you actually have a transmitter and you've got a receiver and you've got a power supply in the middle here. The transmitter and receiver almost look the same, but they are not. They have different controls, and this actually emits the signal and this receives signals off the air. Today, modern radios, in fact, this is a state-of-the-art radio, and our main radio here at WA3VEE, this is an ICOM 7610, which is a state-of-the-art software-defined transceiver, which actually operates on two different frequencies at the same time. This is a transceiver. In this station here, it's feeding a 1,000 watt amplifier, and that the amplifier has a feed line attached to it, and that is attached to an antenna over here. We can also have equipment that looks like this. These are also transceivers. They're transmitters and receivers. This is a handheld. We have some right here. And this is another mobile radio. These two operates on the same bands, and they can either feed a satellite array like this, where we can communicate with amateur radio satellites, or we can communicate as we did down at JOTA at headquarters in front of Horseshoe headquarters, where we're using a straight vertical antenna like this. So block diagram wise, this is what it looks like. In that vintage picture, we had a separate receiver and transmitter, and we could have an amplifier, and we switch between them. When we want to transmit, we disconnect the receiver. When we want to receive, we disconnect the transmitter. And we might have a microphone or a Morse code key connected to the transmitter. Here is a more modern system where we've got a transceiver, as we pictured earlier, that's feeding an amplifier that actually gets applied to an antenna. So radio waves by themselves, unless you turn them on and off, and we'll talk about that in a moment, in a coded way, radio waves by themselves carry no information. So information must be embedded or impregnated onto the radio wave itself in order to have some meaning. So The station transmitter generates a steady radio wave that's called the carrier. Carrier by itself is just a constant amplitude, doesn't change, constant amplitude signal. It doesn't convey any information. So what we need to do is we need to either turn the carrier on and off in a coded way, or we need to change the amplitude of the carrier, or we need to change its frequency. And by doing that, we can put our information onto the radio carrier. So the first way we mentioned was turning the carrier on and off by using a particular internationally accepted set of codes. This is called the Morse code, and this is what it sounds like. That's Morse code, and that's about 7.5 words per minute. And this is what it looks like if you were to look at the radio signal on a screen or what's called an oscilloscope. You would see that the carrier is on for a short amount of time, then it's off, then it's on for about 3 times as long as it was over here, then it's on for it off, on for a short time, off, on again for a short time, and so on. This would indicate an E, a T, an I, a T, and another T in Morse code. This scout here is actually operating a Morse code key at JOTA back in October, right out in front of Horseshoe headquarters. He's actually sending individual letters, and I'm standing on the other side of the table, and I'm actually telling him the letters that he's sending. This is Morse code. This is called continuous wave. You're just turning the transmitter carrier on and off in a special coded way. This is the most reliable communications method in the world. You only need 5 or 6 watts to talk to Europe or Asia most of the time on a particular frequency. And the reason is it requires very little energy because the wave is so concentrated. This is the most reliable method. You can take this, you could take a small Morse code key, a small 5-watt radio, a small battery, a wire, and a tuner, put it in your backpack, and transmit from the mountaintop, from the woods, from the trail, and you could be talking around the world pretty reliably using Morse code. Here's the Morse code right here. This is the International Morse code. And again, in English, what we do is we never say dot and dash. We use the sounds. A would be da-da. B would be da-da-da-da. C would be da-da-da-da, and so on. So we'll get more exposure to Morse code in our classroom sessions. The second method we mentioned is actually varying the amplitude of the actual carrier signal. What we're doing is we are taking a very high frequency carrier signal. Generally, I like to demonstrate this using about a 1 million hertz or 1 megahertz signal. And what we do is we speak into a microphone. Our voice is in the sound region of frequencies. So our voices are very, very, very much lower in frequency than the 1 megahertz carrier. So what we are doing is we're taking our voice or musical notes, lower frequencies, and we are causing the amplitude of this steady carrier to be varied at the rate of our voice or music. So what happens is we are amplitude modulating or amplitude changing the carrier wave at the frequency of our voice. So if we were to look at this on a scope, on what's called an oscilloscope, this is what it would look like. And this is right on my workbench, right on my lab bench at the house. This is the main oscilloscope that I have there. And what it is we're taking this signal right here, spread out cycle by cycle. This is the actual radio carrier. And what we're doing is we're scrunching it up so that all these individual waves are so scrunched up that they become just a kind of a blur inside this envelope here. Let's go down here, it's better. Inside this envelope, this is all filled with 1 megahertz in here, but we're varying that 1 megahertz at a very low, like 1,000 cycle rate in this particular case with a tone. So this is what's known as amplitude modulation, where we're taking a high frequency carrier and we are varying it at a very, very, very low frequency. Then at the receiver, what happens is the receiver takes the 1 megahertz or high frequency carrier, strips it away, and what we're left with is just a variation of the audio. That variation gets sent to an audio amplifier, and then we hear it as music or voice or whatever it is. That's how it all works. The only purpose of the carrier, the radio signal, is to get the intelligence from the transmitter to the receiver. Once it gets to the receiver, it's discarded, and the actual variation of that carrier is kept, and that's what we hear as a signal. Finally, we can vary the frequency of a carrier. If we take our 1 megahertz carrier and we vary it to like 1.1 megahertz or down to 0.99 megahertz, we are modulating, we're changing the carrier again, but we're changing its frequency. So we are frequency modulating the carrier. This is FM. This is how FM radio works. This is what we'll be using later on in our demonstration. And when you get on the air, you'll be actually talking on FM. So we are deviating the carrier frequency from its resting point above and below. The amount of frequency deviation depends upon the volume, how loud our modulating signal is. If it's real soft, or real like a whisper, there's very little frequency deviation. If it's loud, there's a lot of deviation. The rate of deviation, how quickly we're going from the resting frequency to the frequency we're deviating to, back and forth, is the frequency of our modulation. If it's very low, the modulation rate is very low. If it's very high, the modulation rate is very high. Again, the amount of deviation is volume. The rate of deviation is the frequency of the modulating signal. So again, we can either turn a carrier on and off in Morse code, we can vary the amplitude of a carrier, or we can vary its frequency. Those are 3 main methods that we use to put information on a carrier when we send it from a transmitter to a receiver. When it gets to the receiver strips away the carrier and keeps the variation. Digital modulation is very similar to Morse code or CW. What we do here is we either turn a signal on and off, or again, we vary its frequency. And that concludes our requirement of 4 and 5C. The next requirements are 9A3 and 9A4.